recording. All right. December 15, almost Christmas. Okay, so one thing that is kind of not off the topic, but I just want to mention something that I was not able to show you because of the reduced number of labs that we had. However, I feel that this is important that you know this, all right? So what we have, as far as insulation displacement connections, when we dealt with copper cables, copper, okay? This is copper, as opposed to fiber, okay? Links. Okay, let me just here. Just gonna set up my transitions. Excuse me, I like it this way. So we have done toolless connections. Toolless connection, which was when we did the when we terminated the Cat5e cable on a Cat5e RJ45 T568A configuration jack. Remember the toolless with the hinge? We don't need, for that one, we didn't need any punch down tools in order to create the connection. Then when we have done our 25 pair cable, we have terminated the 25 pair cable onto a termination strip that was by BICS, all right? All right, so that's the BICS termination platform. Also, what I want you to know that there's another one that exists that is called 110. These are the termination platforms, all right, that basically we used here in North America. In UK, actually there was one other one that used to be used. It's not as much anymore. In Canada, you can still see some of that in the States. It's the 66 termination platform. And I don't have the termination tool for that. In UK, you're going to see something that's called cron as well, okay? But this is the most you're going to see in North America here that we're terminating, when terminating insulation displacement connectors, RJ45 jacks, or that's not RJ45, that's RJ12. But here is, I'm just going to unpack this RJ45 jack. We're going to see either toolless type of termination, or BICS, which is this, or 110. 110 has nothing to do with the 110 volts that is in the outlet. That has nothing to do with that. Consider this thing as a name. That's a name of the termination platform. Somebody chose that thing to be the 110. All right, so toolless, BICS, and 110. You have done the toolless, you have done BICS, you haven't done 110. 110 is basically the same as BICS. However, the shape of the termination tool and the connector inside the isolation displacement connector is a little bit different. So for toolless, we don't need any punch down tools. For BICS, we need a BICS punch down tool, and for 110, we need 110 punch down tool, and they are not exchangeable. For 66, you need technically you need 66 punch down tool. However, you can just do that with the needle nose pliers. All right, now, I'm not going to show you that. Just Google it, do 66 termination. And you're going to be able to see how that looks like, okay? You're not going to encounter as much of it anymore when doing the terminations. However, it's a good idea to know that this thing exists. You're going to see mostly 110 for data and mostly BICS for telephone. Okay, terminations. So I'm going to show you the differences between these, the bigs and 110. So I'm just going to switch my views here. All right, so first of all, I'm going to show you, let's see if I can zoom in a little bit. Is that going to be better? Yeah, I think it will be better here. Zoom in here. Now, first of all, the shapes of the punch down tools. All right, here's my pen. So this would be 110. This would be bigs. Okay. Now the bigs, as you remember, it has a knife that is it's a moving knife. Okay. Let me just focus. If I press slightly, you're going to see the knife move. Okay. That's where the on one side of the bigs punch down tool, you're going to see the knife that is supposed to cut off the wire that is to be cut off from the termination tool. All right. So when you put that, when you put the wires in the termination strip, when you're terminating, all right. Yeah. Of course, when you're going to punch down with the bigs tool, the knife is going to. This knife here is going to cut off the part of the conductor that is supposed to be cut off, and it's just going to happen like that. All right. Okay. Let's see it again. All right. Now these two conductors are terminated on the BIX platform. Okay. I'm just going to remove that. Now the 110 punch down tool also has a knife, except it's a stationary knife. It doesn't move. All right, it's just looks like this. Can I get better focus or not? Okay, here's the push down. Here's the push down element that pushes the wire into the insulation displacement connector, and here is the knife that cuts things off. All right, but it's not, there's no moving parts here. Okay. So that's the difference. Sorry, that's 110. So here's 110 with the stationary knife, and here's BIX with a moving knife here. Okay. All right. Now, as far as the termination for 110, I just happen to have 110 jack RG45. It's a brand new jack. Of course, doesn't want to cooperate. Come on, cooperate with me, please. There you go. So here's so-called dust cover. And remember the pairs, for example, different jacks are going to have different pairs. This jack is capable of T65A or T568 A or B configuration. So if you look at this jack here, you can see that these two are for the blue pair. These two connections are for the blue pair. For the A configuration, see, this is the top part, A configuration. So you're going to have white, blue, and blue. And over here is going to have white, orange, and orange. So white, blue, blue, white, orange, and orange. And then again, for A configuration, you're going to have white, green, and green. And over here, you're going to see white, brown, and brown. So obviously this is Cat 5E, is it? Yes, it's Cat 5E jack, okay? Because you can see that between the difference between A and B, you can only see that the oranges and the greens are interchanged between A and B configuration, and the blues and the browns, they stay the same. All right? So the way we would terminate this one here is now this lesson is it might go over time. So if you have another class to go to after 11 o'clock, then just go ahead and you can just view this the ending of it later on YouTube. But if you want to stay, go ahead. You're welcome to stay for the rest of this this lesson here. All right. Now, for the for termination, let's say we're going to terminate a configuration. So let's say we have blue, orange, and green and brown. So we're going to prepare. We're going to have blue and orange this way here. And over here is going to be green and brown. It's a good idea to basically prearrange those pairs, so you don't have to later on. You don't have to go all the trip the pairs over each other. So things are not going to get tangled. All right. Neatness is very important when doing data. Okay. Now you're going to keep the twist as you are going to keep this twist as far as you can, right to the punch. So do not untwist that pair. Now, how far should you? How far this tail end should be? It should be long enough so you still have some flexibility, but it should be also as short as possible. Okay. So let's say, okay, so we're going to have white, blue, and blue here. So I'm just going to arrange that. So we're going to have white, blue, and blue. Okay? And I'm just going to precede this. Okay, so here's that. Then the next, once you prearrange that, they all fall in place. Then we have white, orange, and orange. Again, I'm going to just make sure that that the white, orange, and orange are where they're supposed to be. Okay, here it is. Precede that. Okay, so these two are preceded. Now you can continue with the other side, or you can just do the punch down first and then continue with the other side. Your choice, depending on the jack. These jacks come with different configuration by different companies. They come in different physical configuration here. Okay, so now I'm just going to position the knife so it cuts off what it's supposed to cut off and keeps what it's supposed to keep. And you just see if I can do this thing nicely on the camera here, so you can see the cutting action. Now you see this wire, this pair here, the orange pair and the blue pair, they just kind of went a little bit downwards. So I'm going to straighten them out so the knife has a chance to cut these. Okay, and then here I'm just going to cut this. Now you gotta be careful because when you do it this way, the jack can flip on you, and you're going to hit yourself with the knife. All right. Now I have done this thing for 30 years, so I can do it this way. However, there are some inserts or holders. If you don't have a holder, you can just basically you sacrifice one faceplate and use that as a holder. So this way is up. It just shows this way up. And remember, the prongs are always up. See the prongs here? This is the latching clip, and this is where the prongs are. I'm not sure if I can, yeah, there you go. See, you can see the prongs here. So the prongs are always up, and you can see the letterings also. You can match that with this way up. And then you can seat that jack like this here, and then clip it on. This way, the jack is not going to flip on you, and you're not going to hit yourself in your finger. Now, when you hit yourself in the finger while doing the punch down, 110 punch down, it doesn't produce nice straight cut if there is such thing. It just makes it's just going to make a ugly long healing rip in your skin, and you don't want to do that. So now this way here, your fingers can stay out of the way, and you can do the punch down. Yeah. Okay. Now these wires are cut off because you've pointed the knife. If you pointed the knife the other way, of course you would cut off your cable, which is not the point. All right. So here is another. Here's the blue pair. Okay. Now then, I'm going to arrange the other side. And the other side, see, we have pre-arranged the wires. So this is going to be brown and green. So the colors, the white is on this side, and the white is on this side, and the solid is on that on that side here. So just want to make sure, but you can just do it like that too. Put it like this here, hold it, and then undo the twist. So the twist is undone from this side on, and the twist is kept here. Okay? And then you can just precede those wires. Focus, focus. Okay. Precede those, and then we have, oh, they actually align themselves right now. This pair does align itself. So we can hold it here, undo the twist on that side, precede that, straighten those wires up so the knife has a chance to reach that, and then you're just going to do the punch down. Oh, this one doesn't want to, so I'm just going to point the knife a little bit that way so it cuts this off. Here, and the brown pair. Okay. Now we have a terminated Cat 5E jack. Okay. All we have to do is put the dust cover on. The dust cover, it's called dust cover, but it actually prevents those wires from slipping out. Okay. And now we have a terminated 110 jack. Okay, so again, I'm going to ask you on the test about the difference between 110 and bigs. So 110 has a stationary knife and the knife doesn't move, and bigs has a knife that moves. All right, and this is basically what 110 looks like. All right, I'm just going to rip those out. You can see the wires have been. This is how the insulation displacement works. The connector that's inside there bites into the insulation and makes contact with the copper wire. Right? So that's why it's important to do a proper punch down technique. You can't be too wimpy with that. You just really have to show the wires who's the boss, and you're the boss. You have to be in control. So this is what 110 looks like. And this is what Bix looks like. So Bix, you can have termination strips like this. All right. You can also have some of the older version of the jacks in Bix. See the difference between Bix termination? Just get rid of that screw here. The difference between Bix termination and 110 termination strip. They look similar. They both use insulation displacement technique or method of making connections, but they're slightly different in shape. Okay, and they are not interchangeable. If you have 110, you use 110 punch down tool. If you use Bix, you use Bix punch down tool. Okay, So here is the few minutes that I just spent on the big termination tools. Now, from the last, I hope that you have watched the suggested YouTube links when it comes to cleaving and bless you, whoever that was. Cleaving and what is I'm talking about? Safety that has to do with the fiber optics. Okay. Now I'm just going to touch up on some of the cleaving part. Fiber optics. Okay, so here is the fiber optic link. Here's the core, and here's the cladding. Okay, from one elbow. So here's the core, and here's the cladding. Okay, that's where the light travels. Okay, and then there's another one, another. Here is the core, that's where the light travels. There's the cladding that surrounds the core. Okay, they're just like that. All right, just like that. Okay. Now, this is glass. All right. Now, when you break the glass, it shatters. So when you just break the glass, it's just going to be shattered, just like that. Okay. And if you need to splice those two fiber optic links together, it is impossible to do because there's a shattered glass edge on one side and shattered glass edge on the other side. So you can't, there's no way you can splice those. So cleaving is just like chopping. All right. Now, do you remember what the butcher's cleaver looks like? That's what the butcher's cleaver looks like. Let me see if I have my drawing skills. All right. Here's a cleaver. You hold it here and you cleave, you chop the meat. So cutting glass, fiber optic glass, basically has assumed the terminology of cleaving, chopping. So you're not chopping the glass, you're cleaving the fiberglass. Now, in order to cleave the fiber, I hope you watch those the videos that I suggested, and I'm going to go in details on that. But the point of cleaving, what is the point of cleaving? Why do we need to cleave the glass or the fiber optics? Is so we can obtain, my finger's yellow. Yeah, and here, let's just get that. So we can obtain a straight edge here and here on both sides of the fiber optic, of the optical fiber. Once we have the nice right angle straight edge here, nice right angle straight edge here, now we can bring those two together, align them, and then we can splice them. So the purpose of cleaving is to obtain a straight edge at the end of the spliced fiber optic or optical fiber. Yeah. Right. Now we can step into today's topic, which would be the optical fiber practical applications. It's not going to make you an expert, but you're going to actually know some of the terminology, and based on that, you can build your knowledge and experience as far as dealing with fiber optics. Of course, you're going to need to get trained when you get yourself hired in a company that has to do with installation and termination of optical fiber. Right now, installations and terminations using optical fiber. This is the thing to do right now. if you get yourself properly trained, and there's some training facilities that do that, and they keep up with the latest technology as it comes out. So you get the basic training. I'm just giving you the gateway to that. So you know the terminology and you know what's what. That is not going to make you a fiber optic or optical fiber technician yet. All right. However, you're going to know something about it, so you can build up on it. Now, as the technology advances, new technology is going to come out. Different connectors, different fiber optic lines are going to come out, and all the paraphernalia that goes with it. Of course, as you go along, you will be trained as the technology advances. And who is going to train you? Basically the sales reps from the company who sell that. When they release a new product, they make sure that the people are trained on how to use that, so they can buy it. Right. So that's how the sort of like professional development is solved when it comes to going along as you get hired. Okay. All right. Now, here is here's our presentation here. Of course, here's the fiber optics or optical fiber practical applications. What do we see here as the first slide? This kind of reminds us of a patch panel. All right, so except we're not using copper links, wires, we're using fiber optics. So you're going to have a connector plugged in here with the fiber optic line, and connector plugged in here with the fiber optic line. And then through this connector, you can pass on the signal. Now, these white inserts here, they are just dust covers. So they are basically to be removed as you go along before you insert the fiber optic connector. Okay? Cable types that we're going to cover today. We're going to cover cables that are called loose tube, tight buffered, and ribbon. That pretty much goes along with the loose tube, and you're going to see why. Right? Now, loose tube cable. All right, let's see here. These little links here that looks like a spaghetti thing, these are the fiber optic links. It's a fiber optic line, a single fiber optic line. So here's a yellow, here's a green, and there's some other colors here. Now, they are inserted in tubes, okay? Now, how are they inserted into those tubes? They are inserted in a loose way. So they are basically floating loosely. Okay. Now, the reason for that, they're floating loosely because loose tube cables are mostly being used outside, and when you're dealing with outside cabling, then you're dealing with elements. So in the summer it would be hot, scorching hot. In the winter it would be freezing cold. So some of the materials expand or contract based on whether they're heated or cooled. Right. So if you had a tight packed bunch of fibers in a tube, if the tube contracts too much, it could actually crush those optical fibers. Right. So that's why for the outside installations, we are implementing something that's called loose tube connections. Okay, now let's just go over this couple of details that have to do with this here. Number one, which is this thing here. I'm not sure if you can see it, but you'll be able to see it when you download the PDF version of this presentation. So loose tube is a material filled with thixiotropic jelly compound. Okay, now what's thixotropic? It's basically that the material expands and contracts accordingly when it comes to dealing with temperatures. You can expand on that a little bit, more. You can Google what thixotropic is, but basically what it means is that when it's cooled down, it becomes a jelly type of a substance. Right, and when it's heated up, it doesn't go completely into liquid. All right, so it just keeps its form, so the fibers are just there, but they're not crushed, and it doesn't freeze. The thixotropic thing, right? Of course, up to a certain point. Where are we? Yeah. All right. Now the tubes, optical fibers, number 2 here. So these are the optical fibers. Each tube has so many optical fibers in it. Right? So you can have one cable that can carry a lot of optical fibers. All right. Now over here, this number 3 is a central strength member. It's usually non-metallic, and basically it's a strength member. So it keeps the wire nice and cable nice and solid. All right. Then number 4, where do we have here? Now you have core filling and all the paraphernalia that goes with it, and basically that is to do with protecting of the fiber optic links. Okay, different cables have solved, different companies have solved it in different ways, but basically that's the basics here. The loose tube idea is, now some of them are going to have some armored sheathing as well. So there are different, there are many different cable types, right, depending on how and where you're going to use that. But the idea of a loose tube is that the fiber optic links are inserted in the tubes, protective tubes, loosely. And why is it that they need to be inserted loosely? It's so that when the cable is exposed to elements, heat and cold, that those fibers are not going to get crushed by the materials expanding and contracting. You have some playroom around here. Okay. Now, loose tube cable designed for harsh environment conditions in the outdoors. All right, fiber strands floating loosely in the designated rugged tubes. Material contraction and expansion due to temperature changes will not affect the fiber strands physically. Right? Used mostly in the outdoor long haul installations up to 120 kilometers. So we are not talking 300 feet, we're talking 100 kilometers here. Okay? Fiber optics. All right, now, as opposed to loose tube, we can also have something that's called tight buffered cable. Right? Now, this is no different here. These are fiber optic links. Okay. Now, the only difference between these fiber optic links and these fiber optic links that are inside here is for the loose tube. Here. For the loose tube, because of the longer distances, they are mostly used the single, well, basically it is single mode fiber optics, okay, and or optical fibers. And when it comes to tight buffered, I'm going to show you why. Pretty much most of the tight buffered, but you can also have the otherwise. You can mostly are going to see the multi-mode fiber or optical fiber links. Okay. Now, in the tight buffer cables, you can also see some of the multi-mode cables as well. But mostly it's designed for multi-mode cables. So now we can see that those fiber optic links, so there would be the fiber optic links, you can see the cladding here or jacketing, and then coating and jacketing and so on, and they are tightly packed in Kevlar. Okay, Kevlar strength, Kevlar fibers. Kevlar is a material that uses synthetic strong fibers, and once they're packed together, they can provide a lot of protection. Just as a side note, the bulletproof vests are packed with Kevlar, all right, to stop the bullets. Okay. Now, and of course, here is the ripcord, the armored yarn, or like a wool yarn, armored yarn. Basically, it's Kevlar. Okay. And then there's outer jacket, and those jackets are going to have different colors based on what optical fiber is being used, and that's coming in the next few slides here. Right. Now, tight buffer cable, as opposed to loose tube, is designed for indoor applications. It's more flexible. Fiber strands are packed tightly within the armored yarn or Kevlar, wrapped with the outer jacket, so they're tightly packed here. Now, the Kevlar or the armored yarn is tough as far as providing protection, but is also soft enough so the fibers can move a little bit as much as we need. Now, obviously, you would not use this thing outside because of the expansion and contraction of the materials. It could actually crush the fibers. However, the armored yarn is used because in the indoor, you want to have some flexibility. You want to be able to flex the cable a certain way, as opposed to outside. Flexibility is not as important outside as the protection from the from the elements, and it would be all kinds of things. When you have overhead wires that can damage the cable physically, or it could be also other things that can damage the cable physically when you run the cable underwater, including sharks trying to bite on it. Right? Now, tight buffer cable designed for indoor applications, fiber strand packed tightly with armored yarn and wrapped around with outer jacket, more flexible than loose tube, because flexibility is more important than the toughness when it comes to inside. When you install the fiber optic inside, you protect that with conduit. You use the protective measures when it comes to that, installing it inside, but it's much easier to protect the wire inside than outside. So outside cables need to be tougher. Right? Here, and used mostly in the indoor in land environment. Those multi-mode fiber optic or optical fibers, those multi-mode fibers mostly are being used to connect the communications closets. Right, so you can have a closet with so many computers connected to it. You can have another closet with so many computers connected to it, maybe 30, 40, 50 computers. And you can have one fiber optic link between those two closets. So those switches can act as one closet, right? With that one, it's enough to have one transmit, one receive link, and that should be enough. Sometimes a double, two cables are being used. One transmit, one receive, one cable, and another one transmit and one receive if you want to have more data flexibility as far as the throughput of the linkage. Okay, now ribbon cables. All right, now ribbon fiber optic cable are arranged into a strip. Right, so you can see it's also a loose tube configuration. However, those fibers are arranged in ribbons, which allows us to pack more fiber per tube. You see those, just a regular loose tube over here. Those fiber are, oops, here. Yeah, there you go. Those fibers are just thrown in there, and they just lie down. They just lie down. They just lie in there. Okay, lie down. All right. Now, in the ribbon cable, we're dealing with the same thing. However, there is a little bit more strict arrangements as far as the cables put together. That gives you the possibility of packing more cables or fiber optic links per tube. Okay. Now, let's see what else I wrote here. This is a convenient solution for space and weight problems or challenges. The cable ribbons are actually coated optical fiber placed side by side, encapsulated in mylar tape, similar to miniature version of the ribbon cables used in computer wiring. Okay, a single ribbon might contain 4 or 8 or 12 optical fibers, and the ribbons can be stacked up to 22 high. All right, so you can have 22 ribbons here, 22 ribbons here, 22 ribbons. Okay, get the idea. And then each of them could contain up to 12 optical fibers. So that's, you know what, that's a lot of fiber lengths that you can pack in one cable. So here's the ribbon cable. So now you should know what we're talking about when we talk about loose tube, tight buffer, and ribbon. Just as a review for that is the loose tube is fibers laid in the protective tubes, they just being inserted there, and that's it. Now, as opposed to ribbon, the arrangement is a little bit more organized. Now also, when it comes to splicing, ribbon cables could be more efficient as far as splicing, because when we talk about something that's called diffusion splicing and mechanical splicing, which I encourage you to research on your own. Now, fusion splicing is basically bringing two fiber lines together, just like that, in a close proximity, and there's going to be an electrode here and an electrode here, and it's going to produce a controlled spark in order to fuse those together. So it's basically like welding glass. It's a highly precision type of a procedure. Now, when it comes to ribbon cables, fusion splicing can be much more effective because there are fusion splicers that can handle the whole ribbons. So with one fusion splicing action, you can splice 12 cables instead of just one. And when you're talking about the work environment or business environment, if you can do things faster, just as efficient, also if you can do things faster and just as effective and as safe, then of course you're being more efficient. It's when it comes to running business, sometimes it's about the effectiveness because you need that, and sometimes it's just about the money. Okay, so so ribbon cables can be more efficient when it comes to fusion splicing because you can just bring one from the left, one from the right, bring them together. Now my fingers are not straight. I wonder if there's anybody who has. Now, but let's just pretend they are straight, straight edge here. They're being brought together, close to each other, and then with one press of a button, you can have all 12 spliced, fusion spliced, as far instead of just one at a time. Okay? There's also mechanical splicing, and I'm going to try to send you some links when it comes to mechanical splicing. It's also a very popular way of splicing things, mostly in the LAN configuration. Right? Fusion splicing is done mostly with the single mode cables, and when it comes to splicing the fiber optic links in the utility poles, that let's say there's a fiber length that goes 50 kilometers that way and 20 kilometers that way, and then there is that, remember I showed you that little barrel looking device that are hanging, it's like a black barrel hanging from the utility pole. That's called a FOSC. FOSC stands for fiber optic splice closure. all those splices are nicely inserted there and protected and enclosed, protected from the environment. If you need to work on that, you take this thing off, bring it into the into utility van in nice, warm, dry, free of dust environment. This thing is being opened and the optical fibers are being spliced there, and that's using something that's called fusion splicing, which is basically welding, quote unquote, welding glass together. And there's million of YouTube videos you can just do on the fusion splicing or FOSC maintenance, or working on FOSC. You can see that, you can see a lot of that. Now you can see a lot of pictures, but if you're going to get yourself hired in a company that does that, then you're going to have also some training that has to do with the company procedures. Right, now let's keep going. Where did we okay, so that was the ribbon cables that we have stopped at. Okay, now color code when with the fiber optic. So we're going to show you two color codes. One is the fiber optic links color code, and then there's the jacketing color code. All right, so now let's just get the links. So this would be those links here, color coding, as far as 1, 2, 3, and so on. Remember when we had the 25 pair cable copper, there's a certain color code. Well, fiber optics also have a certain color code, and the links are as such: blue, orange, green, brown, and there's a slate, and then there's a white cable. Then we have up to 12, so go red, black, yellow, violet, now rose, and aqua. Okay, number 13 to 24 go the same way, except with the black stripe, except for the white, or sorry, except for the black. Of course, you can't have a black on black stripe on black, so it's just a regular. So if you're a stripe, that means it's 20, cable number 20. So it's a this is 1 to 24 fiber links, and these are those individual fiber links. Now we're going to talk about the jacketing coloring. Mostly what you're going to I just got the message that my mouse is being set up. Thank you, computer. Now when you see things here like OM1, OM2, and OS, all right? Now, optical, O stands for optical link. Okay, so fiber optics. And the M stands for multi-mode or single mode. Right? Now, as time goes along, the technology that was used to produce the fiber optic links has gone, basically it's moving forward. So so there are different type of jacketings that are being used. Now, we're going to analyze the capabilities of the optical multi-mode and optical single mode, as opposed to the copper. Remember that picture? Now, over here, let me just get my mouse. Sometimes it just keeps disappearing on me. Now, the first size here, it's all in micrometers. Okay. Okay. All right. So the first number tells you the size of the core, and the second number tells you the size of the cladding. Most of the cladding here is 125 microns or micrometers or millionths of a meter, except for this orange one that also is used in the military. Now, military configuration, military scheme is a little bit different from the well, commercial or non-military scheme. You are going to deal mostly with the commercial applications. If you get into the military applications, trust me, you're going to get extensive additional training when it comes to that. So let's just concentrate, just to avoid some confusion, we can just concentrate on the commercial grading here as far as the color coding of the jacketing. This is the jacketing color code as opposed to the optical links color code. So that was the optical links color code. And this here is the jacketing color code. Okay. Where are we? All right. So most of the time when you see orange, you're going to basically know that you're dealing with a multi-mode fiber inside. When you see yellow jacketing, which is like here, for example, where is that? Okay, so you see this tight buffer jacketing, that's an orange cable. Right away, you can tell that it's a multi-mode fiber optic line as opposed to single mode. Now, what's the details of that? Then you're going to have to read the label on the cable. Read the label on the cable. All right, so optical multimode 1, optical multimode 2, optical multimode 3, and so on. This is as far as the technology was developing and better cables were produced, or different cables were produced as time went along. All right. The lowest grade would be the optical mode 1, which has a 62.5 microns core and, of course, 125 microns cladding. Cladding is the next layer that surrounds the core. Right? Now, then you go optical mode 2, which has 50 microns, and this is probably the most popular right now. You can still get 62.5 microns as a special order, but it might take you a few days to get that. But if you go to any distributor, when you order 50 microns multi-mode, they can pretty much get this thing to you off the shelf. All right. Now, those would be the multi-mode. Now, then also multi-mode 50 microns. Now, they look the same. So it's a 50 by 125, 50 by 125 multi-mode. And also this one is 50 by 125. Now, how are they different? Well, they are different slightly as far as the technology. So the bandwidth is a little bit different. They have the slightly different specifications when it comes to anything between OM1 to OM4. Right? Then, of course, you can see when we get into the single mode, which is the yellow jacketing, you can tell right away that when you see yellow jacket, that means basically you're dealing with single mode. And you can see approximately, where's my mouse? Approximately 8 to 10 microns of core size. And of course, you can see most of the, pretty much all fiber links or optical links or optical fiber links have the cladding of 125 microns. So you can't tell just by looking at it. You have to look under the microscope in order to see if you want to physically see that. And of course, when it comes to looking into fiber optics, one thing I'm going to tell you, you never take a fiber optic line and look at it straight, okay? Because you don't know where the other end is, and you don't know what the other end is connected to. The other end could be connected into a laser source. And even though that if you point it at your piece of paper or something, you don't see the light, because remember, the light that is being used in optical fiber transmissions is in the infrared region, and infrared region is invisible to the human eye. We still call it light, except the humans can't see it, right? But the energy is still there. So if you have a laser at the other end, and if you look at this thing straight into your eyes, you can have yourself you can make yourself an appointment to a hospital, right? And in that hospital, they can actually tell you that, sorry, but that eye is blind anymore. Okay, for the rest of your life, you're going to have a blind eye. Or if you're lucky, you're just going to have a black spot burnt up in your retina. Yeah. And everywhere you look, you're going to see that black spot for the rest of your life. So never, ever look straight into the fiber optic line. Now, of course, if you have a piece of wire that's this long, and you know where this end is, you know where that end is, yes, you can put it in the microscope and you can look at this, okay? So don't be silly. Right? All right, so this is as far as the colors of the jacketing. Okay? Now, I'm just going to go back to our copper category cable. You see Cat5, let's say Cat5e, all right? The transfer speed as opposed to the bandwidth. What's the difference? It's the digital pulses transfer speed. It's 1 gigabit per second. And the bandwidth depends, 100 megahertz of CCA or 350 megahertz of BC. Remember, CCA stands for copper cladded aluminum. This is the cheaper kind of a cable. Hint, hint. Wink, wink. Okay. And then, why did I give you the hint, hint or wink, wink? You figure it out. All right. Now, then, of course, the BC stands for bare copper, which means this is the link is made out of pure copper. Yeah. And this is the copper cladded aluminum. So the conductor is aluminum and it's coated with copper to kind of save on money. Right? So this will be less expensive. This will be more expensive. And of course, this is the band, the top frequency that you can transmit as far as analog transmission, and the signal still be understood on the other side by whatever equipment. Right? So Cat5e, what we have? We have some twists. So forget the twist for now. We are able to transmit 1 gigabit per second up to 300 feet. And here's the bandwidth. Okay. Now let's say Cat6. We can have 1 gigabit per second up to 300 feet. So that's no different than Cat5e when it goes to further than 180 feet. But if the link end to end is 100 and up to 180 feet, you can have 10 gigabits per second instead of 1 gigabit. So that's the advantage of Cat6. But remember, when you're dealing with Cat6, if you have runs longer than 180 feet, then there is no sense of using Cat6, because after you pass the length of the link of 180 feet, that thing behaves just like Cat5e. All right. So this is a valuable piece of information because you can save some money when bidding on some contracts. You can talk to clients. Some of the networks you're going to just install as you are told, because somebody else got the contract and they just hire you to install that. So you just close your mouth and you do as you're told and you get paid. But if somebody is asking you for advice, or if you're installing a network on your own, then you can look at those specifications and you can save money, because there is no need to pay for Cat6, because the Cat6 is more expensive than Cat5e if the runs are longer than 180 feet. Okay, now these are just, okay, so the distances, we're dealing with gigabit, 10 gigabit, Cat6a, 10 gigabit is going to give you, Cat6a is going to give you 10 gigabit per second, and that 180 feet doesn't matter because it's going to give you full 300 feet. But most of those, you see the length, maximum length, when it comes to copper linkage or links, you are basically dealing with maximum of 300 feet. Okay, so keep that in mind. We're going, even Cat7a is 100 gigabits per second, but only up to 50 feet. Okay, now let's take a look at this here. This is fiber optic bandwidth chart as opposed to copper bandwidth chart. Okay, now let's say optical multimode 3. Okay, optical mode 3 is going to give you 10 gigabits per second. And here's the number 300, but this is not 300 feet. This is 300 meters. So optical multimode graded 3. Optical mode 4 is going to give you 10 gigabits per second bandwidth, but up to half a kilometer as opposed to 300 feet. So you can just tell that fiber optic or optical fiber is way more efficient when it comes to bandwidth than the copper. Why is copper still being installed? Is the green thing, okay, called money. All right, now you can see other optical multimode 1. Okay, now you can that's a 62.5 micrometers. That is going to give you 100 megabits per second only. See that? 100 megabits per second, but up till 200, sorry, up to 2 kilometers. All right. What's 100 megabits per second here? Cat5. All right. Now, Cat5 is kind of becoming obsolete, or actually is becoming obsolete. Cat5e, 1 gigabit per second, 300 feet. Let's see here. 1 gigabit per second. Where do we have 1 gigabit per second? 1 gigabit per second, optical mode 3 is going to give you 1 gigabit per second, pretty much to 800 meters. So it's almost a kilometer. Optical mode 4, OM4, is going to give you same speed, same bandwidth, but up to 1 kilometer as opposed to Cat5e, just 300 feet. Okay, so this is how you read this chart. All right. Now, what is it that I wrote here? Single mode cable is a single strand. So we talked about that already, but I'm just going to read it anyways. So single mode cable is a single strand of glass fiber with a relatively narrow diameter, about 8.3 to 10 microns. So single mode fiber. Okay. Usually it has one mode of transmission. And remember, with mode, we were talking about the angle that the light is hitting the fiber optic link, and it gets into fiber optic link and it travels pretty much in a straight line. Of course, it's going to have a little bit of reflection from the walls, but it's considered as negligible. Now, when it comes to multi-mode, you're going to have light hitting on different angles. These are the different modes, and they're going to be bouncing off because the core is much wider than the single mode. All right, the multi-mode is much wider. So of course the light is going to be bouncing off. Now think about it. The signal sharpness, or the sharpness of the pulse, is going to stay sharper in a single mode because it's not bouncing off the walls. Now, when it comes to single signal sharpness or intelligibility or integrity, signal integrity, that is in the multi-mode. Of course, some of the light that goes in a straight line is going to get faster to the end, and some of the slightly higher angle, it's going to take a little bit more, it's going to take a little bit longer because it covers more distance because it's bouncing off the walls, of course, the distance. And now, if you have a high angle, then the light is going to keep bouncing a lot. So the signal, if it's like nice razor blade sharp at the beginning, it's going to be a little bit faded or blurry at the end because of the angles of the light reaching the end at different times. Okay. Now, what was I talking about? All right, so this is the single mode. Usually it comes with mode of transmission that propagates in the waveform in 1310 nanometers and 1550 nanometers. Now, this is something I want you to pay attention to. Just keep these two in mind, 1310 and 1550 nanometers. On that account, there will be a little light reflection when the light passes through the single mode fiber core. So this is basically what I said. You know, it travels in light travels pretty much in the straight form. Yes, it waves just a little bit because nothing is perfect in nature. The nature is perfect in nature, but nothing is perfect in nature that is sub to nature. Okay, whatever. Okay, now, consequently, it will reduce the fiber attenuation and optimize the speed of transmitted signals. What's attenuation? Not attenuation, it's attenuation. It's basically the signal degradation as it travels along. Okay, so because it's the light is stronger, well, that's one thing. It travels in a straight line and it doesn't bounce off the walls. Signal is going to stay strong further than the multi-mode. Okay? For single mode fiber optic cables, no matter the data rate, it's 100 megabit per second. And remember, I'm saying megabit. When it comes to data speed, we're talking megabits per second or bits per second. When it comes to storage, we're talking bytes per second. Okay. Now, for single mode fiber optic cable speed, no matter data rate is 100 megabits per second or a gigabit per second, and transmission distance can reach up to 5 kilometers. Now, this is an arbitrary number depending on who says that and what do they mean by that and what kind of a signal parameters they're considering. Because over here in this example, it says 5 kilometers. In some other example, you're going to see something like 100 kilometers. Okay, so generally speaking, multi-mode cable, single mode cable, single mode optical fiber is good for about 100 kilometers of a distance. Now, in that case, it is usually used in the long distance transmission. Now, we're just going to take a quick look at the connectors. When it comes to connectors, these are the practical applications. Now, you see, just on the top left corner here, you can see yellow jacket here. What does that tell you? What does this tell you? It's a single mode. If it was a orange or aqua, which is like a light blue color, it would be a multi-mode. Okay. Now, most of the time you're going to see SC or LC connectors. SC are bigger and bulkier, and they are all there. Then the LC connectors are smaller and newer. Okay. Now you can you can read this here. Should I read this thing? Okay, why not? SC stands for subscriber connector, and it's a standard duplex fiber optic connector with a square modeled plastic body and push-pull locking features. SC connectors are typically used in data communications, cable TV, and telephony environments. SC snap-on connector also with 2.5 millimeters ferrule. What's a ferrule? Ferrule is this piece here. That's a ferrule, and it extends all the way up to the rear of the connector when the connector meets the optical link, that the optical link is inserted and crimped. This is a mechanical connection. It's not a fusion splicing, right? There is no heat involved. Just the cable is inserted in a precision type of way and crimped. All right, so well, I just want you to know that these are the SC connectors. These are the LC connectors. These are much smaller. LC stands for Lawson connector, is a small form factor connector that uses 125 millimeter ferrule, 125, 120, sorry. Okay, my numbers, my mouth, my brain connection to my mouth, 1.25 millimeter ferrule. So Here's 1.25 millimeter diameter here. Okay. So you see here the ferrule here is diameter is you're talking about 2.5 millimeter ferrule, and then it's 1.5 millimeter ferrule right here. Okay. Now these connectors are much smaller. If you have smaller connectors, you can pack them in those trays. You can pack them much tighter, so you can have more connectors per size of a per certain space. So you can have more LC connectors as opposed to SC connectors, the size. Okay. So most of those types, you're going to use either these SC or LCs. And now there used to be some older connectors, ST connectors, straight tip connector. That is the old connector. You may still see some of those in some of the older installations. So just so you know that what that is. Okay. Now, remember what typical wavelengths. Okay, now here's a statement and a half. Okay, so here's a statement and here's a half. Sorry. Okay, while it is common to use frequency in hertz to specify the transmission band in radio communications, in optical fiber communications, we are talking about wavelengths in nanometers. It's just the way that the terminology has set into the usage of the industry. Okay? Now, keep that in mind. Right. Now, typical wavelengths here. Typical wavelengths, 850 nanometers, 1300, 1550. Most typical ones would be 1300 and 1550 nanometers wavelengths that are being used while transmitting the oops, that's not the end yet. Okay, while transmitting the signal over the fiber optic links. Why do we have these and not the other ones? Okay. In optical fiber link, as I said, nothing is perfect in nature, and we're trying to, the technology tries to establish things that are as perfect as possible. But for the most part, you're going to have an optical link that is made out of glass, or it could be plastic, because the plastic technology has gone as far as you can actually use that thing for fiber optic links. But let's say it's glass. Right? Glass, while being formed, the kind of unwanted side effect is that as much as you try to eliminate that, you still are going to have some moisture trapped in the glass as the glass is being produced. So moisture means water particles. Now, when you are transmitting certain type of wavelengths, as far as light that goes through the fiber optic line, certain frequencies are reacting with the water particles that are trapped in the glass, and they interact in a way that somehow the water particles just absorb that light. So they just basically make the light disappear. So those wavelengths should be avoided because the efficiency of transmitting a signal from one end to another, it just goes basically down to zero. So those wavelengths should be avoided. So that's why when you see the absorption region here, so there'll be absorption here. 1330, sorry, 1300. So no, okay, sorry. The absorption peaks, these are the green nipples right here, okay? These are the peaks of absorption. So between 850 and 1300, somewhere here in the middle, you're going to have the light being absorbed and basically blinded. The light is going to disappear into the water particles, and over here as well. See, as close you get to somewhere in the middle of that, the absorption gets really high. So this is basically almost like blinding the light completely. The light disappears, and anywhere here is just less efficient. So, and in 1300 and 1550, around those two frequencies, the light is not affected, but by the light, by the water particles that are trapped in the glass. So that's why those are the common frequencies, or around that being chosen for the optical transmission. Now, when it comes to scattering of the light, scattering the water particles that are inside that, they instead of absorbing the light, they reflect them and they scatter them all over the place. So yes, you're going to see some light, but the signal is just basically useless. All right. So also that should be avoided. Those frequencies should be avoided right here. Okay. Lower than, so the scattering goes, so the 850 nanometers are not as much, so they are not going to be absorbed by the scattering. Is so you can still transmit the light, but it's not as efficient. So the best efficiency you're going to get from 1300 or 1550. You see the scattering is much less. See, that's the scattering graph here. The scattering of the light is much less at those frequencies at 1550 than 1300, but still usable. And there is no absorption. So that's why. Now, I just have another table here, plastic optical fiber, POF, or the multi-mode graded index, or single mode. And this would be the typical wavelengths that are being used. What's a plastic optical fiber? Well, it's made out of plastic. Multi-mode or graded index. We didn't have time to cover that. But I encourage you to research that on your own here. Okay, and then there's of course single mode. So these would be 850 nanometers, 1300 nanometers for multi-mode. And for single mode, yes, you can still see, well, 850 and 650 nanometers are not used at all for single mode. 1310, anywhere from 1490 to 1625, and then 1550 is the typical wavelength. Now, by saying that, when it comes to absorption, the technology keeps going and it improves as we go along. There are optical links that are made that the absorption regions do not exist, and they are called the full spectrum optical links. Okay, they are much more expensive. They're being, as time goes along, they're going to become more and more popular. So this way, that opens more possibilities of greater bandwidth being distributed, as far as carrier frequencies being distributed along the bandwidth that is available by the fiber optic link. There are those fiber optic links that are being produced, and they're called full spectrum. Okay, now that basically concludes our journey. It was a pleasure to work with you. Now, there are a couple people that are going to see me tomorrow in the labs that are going to that they have missed. And I hope to see you sometime in the hallway around the college. And don't be a stranger. And if I just walk by you, because it's just me, because I don't know, I have tendency not to remember people's faces, especially when everybody has their masks. If you just see me not noticing you, just give me an elbow or something. Just say hi, Mr. Bach. Can you see me? I go say, yeah, I can see you. All right. Okay. I hope you find this this course useful. And if, as I said in the beginning and throughout the course and now, if you decide to go in business for yourself when it comes to telecommunications or this part of telecommunications, by all means, drop me an email. I can give you all kinds of advice. I've done this type of business for the last 30 years. Or if you get yourself hired with some companies and you come up to some sort of a problem that you're going to have, you need some advice solving, also drop me an email and I'll do my best to assist you with that. Okay. Other than that, it's been a blast. Thank you for participating in this course and hope to see you again, maybe in some other courses in our college. Okay, so that's it. Um, Live long and prosper, something like that. All right, see you guys. Oh, test. I'm going to distribute. I'm going to um, open the test later on in the evening, and you're going to have until the end of the week to do the online test, and that's going to be the end of this course. Okay. Other than that, you know my email. See you guys. Bye.